Uh-oh. Um, you can maybe hear us?
Yeah, I can
Uh,
hear you.
I don't know why my video is turned off. Um, like literally my camera is right in front of me. But there's a few of us in our main conference room, so let me try and get um, video turned on for that. Have you tried to share your screen just to see if it works?
Okay, just wait a second.
And this is Ben talking, by the way, since you can't hear me or see me.
Okay. You can see my screen, right?
Yep, yeah, that
Okay,
looks great.
okay.
Um, why is video recording not work or video? Um, the whole point of me coming to the conference room was to have you be able to see us together and it look like a normal seminar to people. Um, for some reason, my videos. Hold on, let me try this. I think it's yeah, yeah. My camera somehow thinks when I'm connected that it should use the camera from the room. I'm working on it. It does, but it's not going to connect on the MacBook. Um, oh wait, maybe it's fine now. Haha, it's fine now. Ah!
Video settings, what do you have options?
I think I'm just totally frozen now.
Yeah. So it looks like something bad is going.
Oh wait. Actually, why don't you join mute
And just put the camera? Yeah.
just so yeah. No, just one. That's fine. So sorry, I'm very bad at computers. So I just for a little bit of background, how long have you been at Georgia Tech?
Oh, so this is my last year.
Ooh.
Yeah, so
So
you're getting to graduate.
do you know what you're doing next?
So I will start a postdoc at Zurich, ETH Zurich, with Kennison Patterson.
Oh, he's
Kenny.
awesome.
Yeah, yeah.
Um, I right there's very few people who can like switch between theory and applied and back quickly, and he's really good for that.
Yeah.
Um, yeah, I just remember we had a practical or like there was like a practical session at crypto a couple of years ago, and he asked every paper, "Do you have an implementation?" And the answer to 3 out of 4 was no. And it's like, why is this the practical session? Um, uh,
Is there a place that I should be?
no, because I'm frozen. So,
Wherever you want.
um, so we'll. And by the way, I've been saying it is Johnson. Is that how bad is that?
Sorry?
Your first name, Tianxin
Yeah,
or
Tianxin.
okay.
Yeah.
Um, hey, Amir. So we'll wait one or two more minutes. There was as I said, there's a an engineering faculty meeting that was just finishing up, which is why we moved this. Am I looking at that? And just as I'm, just so we're kind of visible. Okay, we're kind of visible. So I know Georgia Tech had also been struggling a little bit with COVID. Are you TAing or anything this semester?
No, because this is my last semester, so basically I just work at home.
Great. Um, okay, so we've got, I guess, some of our group in person, and I think we'll have faculty coming on soon. So this is a little bit of a selfish presentation because we've been working on super related things, and I saw this paper come on ePrint a couple months ago, and I'm like, oh, these are people who are 6 months ahead of us and have already like thought about all of the design issues for this. So yeah, super excited to have Tianxin here, talk about a little bit of searchable encryption, how it messes with noisy data and the intersection between those two things. Do you want questions during, or do you want people to wait, or what's your preference?
Maybe wait at the end of the talk. Is
Okay,
that fine? Or if there's a question that you need to ask, you need to be answered at once, you can just stop me.
okay,
That's
great.
fine as well. Yeah.
All right,
Okay.
so with that, go ahead, take it away.
Okay.
And thanks so much for being here today.
Okay. Just, so, hello everyone. So I will start my talk on privacy preserving approximate KNN search that hides access query and volume patterns. And this is a joint work with my advisor, Sasha Bulirava. So let's first get started by looking at what KNN is. It's defined as over some metric space given data sets, can we construct data structure that returns a point, which is the i's nearest neighbor of the query point for all I from 1 to k. And you can see that in this illustration, suppose q is a query point and all the red points are in the data sets. Then for k equals to 2, and we say that P1 is Q's 1NN and P2 is Q's 2NN. As we all know that KNN is a basic machine learning technique that has numerous applications, including content-based image search, face recognition, medical diagnosis, and anomaly detection. However, the issue is that nowadays, high-dimensional data such as pictures, videos gets more prevalent, and finding the exact KNN suffers the inefficiency problem. And thus we turn to another problem, namely AKNN, which is appropriate for those applications that allow sacrificing some precision for efficiency. And we define the approximate KNN problem, or epsilon delta AKNN here. We ask, can we find points that is no more than 1 plus epsilon times the distance of the two i's nearest neighbor with probability at least 1 minus delta for all I in 1 to k. And in this illustration, you can see that suppose k equals to 2, epsilon equals 0.2, and P1 is Q's 1NN, and the distance between P1 and Q is R1. And we say that P1 and P2 are Q's approximate 1NN because both points are within the 1 plus epsilon times R1 distance thresholds, namely the orange circle. And similarly, suppose P2 is Q's 2 and then the distance between Q and P2 is R2, then we say that the P2 and P3 are Q's approximate 2NN. Since we have enough background knowledge on the problem we want to solve, next we need to establish the problem setting we are working with, specifically the outsource setting, where the client has the data and secret key. In this illustration, let k equals 2, the client will first encrypt the tags and associated files and send the encrypted database to the server. Later, when the client wants to find the KNN of her query tag, she will send the query to the server, and the server will reply its queries AKNN's associated files. So in this example is the blue tags are getting matched, and the associated files are returned to the client. So such encryption explicitly targets auto-setting, offers privacy-preserving solutions for accessing the inquiry data. There are a couple of SE schemes that support KNN queries, and we list the reference here. However, no SE schemes mentioned above provide strong security guarantees. Some leak the relative distance of the underlying data points in the ciphertext, and some leak the query pattern, and sometimes volume pattern and access pattern, which we will explain in the next slide. So for volume pattern, it means that adversary can glean information, for example, the number of matched encrypted files by observing the transcript size. In this illustration, the orange query has 2 matched orange files, blue query only has 1 matched files. The query patterns implies whether the queries are repeated. So orange queries have been made twice in the picture, and the access pattern implies what encrypted files that client has accessed on the server. In this case, the adversary can know that the 2 orange files have been accessed twice, 2 queries have been made twice, and the associated files have been accessed. So these are the common leakage patterns of SE, and initially people were okay with that as it provides as fast SE solutions. But in recent years, emerging attacks exploit the common leakage patterns, have successfully recovered the queries or reconstructed the dataset. So you may wonder, is there any more secure KNN solutions without leaking those common leakage patterns? The answer is yes, but they rely on strong assumptions. For example, Oblix uses secure hardware SGX, and there's another secure KN scheme relies on non-colluding servers. And that's why we asked the following question: can we have a practical secure approximate KN protocol that hides access, query, and volume pattern in an outsourced environment? Because we are trying to hide the access pattern, and it is well known that Oblibus RAM, a very strong but communication-heavy cryptographic primitive, hide the access pattern. Namely, the adversary cannot know the logical addresses of the memory blocks by observing the memory access. However, the bad news is that Navid in 2015 showed negative results that directly composing SE with ORAM neither hides the access pattern nor provides an efficient solution. In other words, it costs more bandwidth than transferring the whole encrypted database for a single search. Luckily for us, we observed that solving AKNN with ORAM-based constructions is more feasible than general keyword search, since the number of data points or documents associated with each query tag can be bounded.
Sorry, can I ask you a question there?
Yeah.
So I get why ORAM wouldn't be efficient. What does it mean that if you take searchable encryption and you add on ORAM, it doesn't hide the access pattern? Well, I guess, yeah. I'm not sure how to interpret that statement.
Okay, so because directly composing SE with ORAM, so the SE itself actually leaks the access pattern. And if you want to compose it together, then it will still leak the access pattern.
Oh, so you're talking about basically where like an identifier is returned and then you use ORAM to look up the actual record.
Yeah.
Okay. Then...
So yeah, it's not clear in that, but thank you for the question though.
Okay, great, thanks.
Yeah. Okay. So our contributions for this work includes defining security of privacy-preserving AKN protocol, or PPAKNN, define security of oblivious map with encryption, or OMAP-P, and we construct a generic PPAKN protocol based on OMAP-P, and the OMAP-P constructions based on oblivious AVL tree and oblivious biscuit list. We then conduct security analysis of PPAKN constructions and evaluated the efficiency through implementations and experiments. Before going into the details of the construction, let's move to define the syntax, which is part of the standard privacy security paradigm. A privacy-preserving AKN protocol, PPAKN, is defined for metric space, message space by two algorithms, setup, decryption, and two interactive algorithms, search and update. I have made some illustrations for the setup, search, and update algorithm and made the decryption as it is more straightforward. For the setup algorithm, the client will input the epsilon delta, which is part of the AKNN correctness, and the auxiliary information Z that contain some parameters of the distributions, and a list of tags and social files. Setup algorithm will then output the inquiry database, a secret key, and the Kmax, that is the largest key supported by system. The inquiry database will be outsourced to the server. For the search algorithm, it works as follows. The client will input her secret key, a secret key that is 1 to the Kmax, and her query tag, and the server will input the inquiry database. At the end of the search algorithm, the client will receive the associated files, and the server will update the inquiry database. The update protocol works similarly, as the client will input her secret key operation that is either add or remove, her query tag, and the social files. The server will input the inquiry database. At the end of the update protocol, the client will receive no output while the server will update the inquiry database. We require the following correctness. That's we want a epsilon delta correct for search and perfect correctness for both update and decryption. As for efficiency, we want a big O of polylog n computational and a big O of polylog n communication bandwidth, assuming Kmax is much less than n, where n is the number of items in the dataset. So for the security definition, we provide a simulation-based security notion with leakage functions for setup, search, and update. We define the real and ideal experiments. In both experiments, the adversary is given the inquiry database. It can adaptively choose the queries, receive the function outputs, and the transcripts produced by the honest executions of the real protocol in the real world. In the ideal world, the simulator needs to produce the inquiry database and the transcripts based on the allowed leakage. Our definition requires that there exists a PPT simulator for every non-uniform PPT adversary A. A can only distinguish the real and ideal world with negligible probability. We model the server as an honest but curious adversary, but we require that once the server is compromised, the inquiry database should be resistant to the snapshot attack. Namely, no efficient adversary is capable of learning the underlying plaintext by examining the inquiry database. So if constructions satisfy our security definition, then it implies that all PPT adversaries cannot learn information other than the allowed leakage explicitly specified in the constructions. As for our constructions, we show that the leakage profile is essentially contains only public parameters. So to build a PPAKN constructions, we need to study how to solve the unsecured AKN first. We found in the literature that we can solve AKNN by reducing it to a list of subproblems denoted by denoting the blue blue boxes, and I will explain in the next slides. So we solve each subproblem with an algorithm called ELSHCRNN. Then we can solve the ACAN problem. This is a known idea, but with no practice proof. So we provide one in this work. First, we need to define what the approximate near neighbor problem, or CRNN, is. That's where the C is the approximation factor, which is normally set to 1 plus epsilon. And we use some similar graphs that we defined ACAN earlier. And you can see that this is a decision problem with extra outputs. It asks the following question: is there any point within Q's R radius? If it is yes, then returns point in the dataset that is at most C times R far away from Q, which is within the orange circle. Now, yes. Then if there's no such point, then outputs no. So in this illustration, suppose C equals 1.2, and the distance between Q and P1 is R, and we say that P1 and P2 are Q's CRNN. And how to solve CRNN? Now we use a algorithm called ELSHCRNN that we first need to define what LSH is, then define its extended version we call ELSH, and then describe how the algorithm works. For the plain LSH, or locality sensitive hashing, essentially it's a vector of random hash functions, and the closer the data, the more likely they share the identical hashes. And the extended version of LSHE, so instead of have only one hashes, we say that can we have they share at least one hash out of, say, the L here, and we say that they're close. Otherwise, we say it's far, and we use more illustrations to clarify the concept. This is a simple example where for Hamming distance, suppose vectors I and I prime, those are closer data, and we have we computed them 5 random hashes, compute 5 random hash functions, and above H1 to H5 are the hash outputs. And you can see that for I and I prime, they share 2 identical hashes, and we say that these 2 vectors are close. But for the far data, there's no hashes that are identical. So we have ELSH ready. Let's move to the ELSH-CRN algorithm. So ELSH-CRN algorithm uses a lookup map and finds CRNN by examining points sharing overlapped ELSH text with secure point. For simplicity, we just use the following figure to denote the algorithm with the lookup map. And all I have mentioned before are for unsecured KNN solutions. So how to build a secure one? The idea is that, yeah.
Can I ask you a question before you go on? So, as you presented, ELSH is the error rates associated with it are if you store one thing. Do they naturally generalize to, I've now computed this many hashes for a set of, let's say, n things?
Sorry, I don't understand the error rates here.
So, right, the probability, right, you're talking about at least one hash matching for nearby things and no matches hashing for far away things.
Yeah. Yeah, it's just with probability. Yes, it can include those false positives.
Okay, I think I'll ask this question later, or
Okay,
maybe
okay.
not at all, but okay, thanks.
Okay. So let's move to define, so how to construct a secure one. The idea is that we can instantiate the lookup map using oblivious map with encryption. So oblivious map, there's already two constructions before. One is called O-level tree and the other is O-biscuit list. However, they didn't concern them. They only concerned the obliviousness of their construction, but didn't address the data privacy in their secure definition. So we define a new one called OMAP that combine the two constructions with standard symmetric encryption or mode operations, and to address both obliviousness and data privacy. So to build a OMAP, we need building blocks: oblivious map, that is oblivious AVL tree, and O-biscuit list. And both implemented using non-recursive position-based ORAM, or for example, pass ORAM. Then we build OMAP with oblivious map with symmetric encryption. SE, essentially you just encrypting each block or nodes and re-encrypting when accessing and writing back the blocks. And I can give a general overview on how oblivious data structures work. So for the, you can see this is a tree structure, and to implement the, say, the OAVL tree. And the client will start from the root node, where the root node has a label or the key field of the map, and the documents are stored in the value field of the map. So for brown tag trying to find this associated files, they will first compare it to the green tag. Say if it's larger than the green tag in value, we will go to the right pass. The right pass will first retrieve the right position. So this is the civil one. And it will retrieve it from the server side. And then it will still compare the brown tag to the silver tag. And we found that it still needs to go the right path. And then finally it will retrieve the correct or the matched documents from the server. So when we can just write it as a list of executions of the protocol, first sending the silver tag because we found we need to go to the right path to the server, and the server will return the corresponding node, and then the brown tag, which indicates the position maps, and the server will return the corresponding node. And finally, the client has found the matched files, and she will need to re-encrypt those nodes and send back to the server. This ensures both data privacy and obliviousness. So for the security of OMAP constructions, it is stronger than structured encryption, as it also hides the type of the update operations, namely whether it's an add or remove. And for the leakage, essentially the access protocol, the leakage is empty. And the setup contains the public parameters of the oblivious map, including the number of nodes, tree height, node size, and bucket size, which is part of the underlying ORAM parameters. And OMAP constructions hides access, query, and volume pattern. So we have the OMAP construction. Let's move to the how can we build PPA KNN. For the PPA KNN construction, the client will first using OMAP key generation algorithm and generate her secret key. And then it's compute the parameters using epsilon delta part of a KNN and Z the parameters of the message distributions, and it will output the EL search parameters and also Kmax, the largest K supported by this system. Then the client will run the extract EL search tags taking input her documents and the EL search parameters, it will output those EL search tags that can be used for EL search DRNN. Based on those tags and associated files, we can construct the EL search maps. And the maps will be fed into the OMAP setup and outputs the OMAP encrypted map that outsourced to the server, and the root node is stored in the client local storage. As for the PBAKN search and updates, it works similarly. For the search algorithm, essentially the client will run the OMAP access as a subroutine several times, and it will return the associated files. An update also is just run the OMAP access as a subroutine several times. The correctness and efficiency aspect for the construction, the correctness is not straightforward. But we provided proof on correctness and the upper bound on the size of returned results for efficiency. As for the efficiency aspect, you can see that the client storage is just a constant size of the root node. So the permanent client storage is a constant. And the overall bandwidth for search is big O of Kmax times log n square. And the computational complexity, the clients perform AES-based encryption and decryption in the big O of log square n times, and the linearly compute pairwise distance in size of Kmax. And the server only needs to read and write big O of log n memory blocks for each AKN queries. And we proved that our PPAKN construction, the security, relies on standard cryptographic assumptions, namely INCPA of SE and adaptive obliviousness of the underlying obvious map. And it's stronger than structured encryptions as it hides update operation types. And the leakage of our construction for the setup, it only leaks the public parameters of OMAP, and both search and update leaks the number of executions of OMAP access respectively. So we can conclude that our construction hides access, queue, and volume pattern. And we completed our PBAKN protocol, incorporating the ELSearch library, ELSearch kit, together with two new implementations of OMAP, OVO-tree E and OBISCUBLE. We tested and selected the ELSearch parameters on benchmark datasets. Let's continue on this slide. So those 4 datasets that we tested are all high-dimensional data points in the Euclidean space. We ran the parameter selection algorithm provided by ELSearch kit for 1,000 queries on the training set of size 60,000 and finding approximate 10 nearest neighbors, namely Kmax setting to 10. We selected ELSearch parameters with low cost, the fraction of number of data points shared the identical ELSearch tags as queries, the lower the better. And high recall, the fraction that the number of correct AKN captured in the response set. So we found that fixing L to 10 epsilon 0.1 is enough to for a sufficient high recall across the data sets.
So, sorry,
Okay.
maybe now I can try and ask the question. So the number of items in the data set shouldn't affect recall, but it would affect precision, right? Because as you have more things with LSH outputs, you're going to get more matches that you shouldn't.
Yeah.
Okay.
Yeah, what's your question then?
Well, so maybe my question is like, your selection of ELSH parameters was to hit a particular recall level, and then you didn't worry about precision for that recall level.
Yeah, because for the false positives is we just want a bounded data points associated to that. So we don't want a probably unlimited data points. Otherwise, it's not meaningful for the LSH, right?
Ooh, okay, yeah,
Yeah.
but okay, great. That really helps. Thank you.
And we have two optimization methods for one is batched queries and the other is parallel access. So for the batched queries, we proposed a modified search algorithm that aborts the search early if enough points are found, and this yielding a multiplicative factor improvement in bandwidth. And then the other is parallel access. So it will reduce the number of round trips by the factor, the number of OMAP instances available on the server. Just to provide a illustration of the efficiency evaluation here. So we set the user cache size as 10 megabytes. And you can see that the baseline we are comparing with is just downloading the inquiry database as a whole for one query. And you can see that the blue one denotes the overview tree construction, where the darker one is with parallel access. Similarly to green ones denote the OB-Skibli, the darker one with parallel access. And the OB-Skibli based construction performed better than overview tree E-based one across the datasets with fewer round trips per AKN query. And using parallel access reduced the number of round trips by a factor up to the total number of OMAP instances available, so 10 as in this graph. We also need to evaluate the bandwidth cost. Similarly, we have the one is without the optimization method, and the other is with the batch queries. And you can see that OB-Skibli construction, denoted by the green bars, performed better than the overview tree E-based one. And both instantiations perform better on SIFT and GIST with 1 million data points than the smaller dataset, minutes and fashion minutes of size 60,000. And optimization with batch queries increased the number of supported AKN queries up to 10 times shown in the graph. So for a much larger database or smaller Kmax, the offset compared with the baseline increases, since the overall bandwidth overhead is big O of Kmax times log n squared, where n is the number of items stored in the OMAP. So this concludes my talk. And if you have any questions, you can just ask me then.
So let's thank Tianxin first. I don't know who else is here, but I want to give other people well, maybe I'll ask one more and then I'll ask a question. So for all those data sets, you're using L2 distance, or like
Yeah.
okay, so you're not using any feature extractor, or you're using some standard feature extractor, or...
Oh, so the database itself are the feature vectors. So you can see that the say the GIST and SIFT those are the feature extractors. Those actually are the algorithm used for the features. So the database only contains feature vectors.
Oh, okay. Okay, good. And I guess follow up on that. So like for Euclidean distance, do you know like roughly what the underlying error rate of these feature extractors was?
So we are not worried that much of the. So what do you mean by the error rate of the feature vectors?
So what's the distance parameter for right? So you had this CR nearest neighbor, and you said what's the radius for that? Is what I'm asking.
Okay, so I think that's the main thing between there's a gap between the theory of LSH and also the practical side of LSH.
Yep.
Because the main difference is for the theory part, it will have no a background knowledge of the data distribution.
Yep.
But for the practical side, we have the training set. So you can compute the parameters using the theory, but it will only guarantee I guess it's just a lower bound. So for the practical side, you can actually perform better than those lower bounds. Are you getting what I'm saying? So you can set parameters based on radius, theoretically, but you can also just perform the parameter tunings on the training set to get a better performance than what is guaranteed by the lower bounds in theory.
Okay. Okay, I wanna stop for a question and let other people
Okay.
ask questions. And anybody? That's Chloe quietly talking.
Sorry, yes. No, I was saying, yeah, so like the question, like the parameter selection was my question.
So, I guess to follow up on, so your this OMAP-E you said can be built. Basically, do you immediately inherit any advances in position independent ORAMs for efficiency there, or is it tuned to like the ORAM or the path ORAM construction itself?
So the OMAP construction. So basically, what the OMAP-E or the obelisk map we are using are based. The building block is non-recursive positioned, position-based ORAM.
Okay.
So yeah, I don't know. Can you repeat the question because I'm not really getting
So
it.
the question is just, are you using that type of ORAM as a black box? And I think the answer is yes.
Yeah, non-recursive position-based ORAM.
Okay. Good. I think that's the questions I have, especially since we're gonna talk in like an hour in a smaller community. But anybody else on the phone?
No questions, but just wanted to say thank you for the excellent talk.
Oh, thank you.
Yeah. Yeah, that was really great. Thanks so much, and I'm excited to do a bit of a deep dive in a little bit. But I really appreciate the time.
So will we meet directly after this seminar or?
Oh no, sorry, I've gotta do a silly like grant management thing. It's not silly, but I gotta do a grant thing. So the hope was 2 o'clock if you can do that.
Okay, that's fine.
Okay, great. Thanks very much. We'll talk in a little bit then.
Okay, thank you.
Yep.
Thank
Bye.
Bye.